Hi, my name is Jacob Windel. I'm one of the co-authors of the Mind Action Series textbook range. Lately, we have received a lot of questions from teachers about increasing and decreasing functions, and specifically about whether we should include or exclude the stationary points when writing down the intervals on which a function is increasing or decreasing. In this video, we will discuss firstly the formal definition of increasing and decreasing functions over intervals and at points. We will secondly discuss how we can use calculus to determine where a function is increasing or decreasing. This is the way we do it at school level. And finally, we will discuss how you can explain this in an easy and effective way to your learners. Let's get on to it. What you see here are the formal definitions of increasing and decreasing. This is how it is taught at tertiary level. So this is not how we teach it to our learners at school level, but these are the formal definitions. So whatever we do at school level has to be in agreement with this. Let's read the definition for increasing. A function f is increasing on an interval I if for any two values xl and xr in the interval I, with xr greater than xl, it is the case that f of xr is greater than f of xl. Now, what does this mean? It means that if we pick any two x values in an interval, one on the left and one on the right, that is why I use the subscripts L and R here for left and right. And that is indicated by this part here. XR is greater than XL. Now, we know if one x value is greater than another, the x value that is greater is on the right. So XR is greater than XL. That means XR is the x value on the right and XL is the x value on the left. Now it says it is the case that f of XR, so f of the x value on the right, is greater than f of XL, so f of the x value on the left. Now remember, f of x means y. So it means that the y value that we get from the x value on the right is greater than the y value that we get from the x value on the left. Now, as long as this applies for any 2 points in an interval, we say that the function is increasing on that interval. Now, if you look at the sketch here, what we have here is an increasing function. Now, basically, we know that increasing means that the graph is going up. As we move from left to right, the graph is going up. Now, obviously, formally, that means that the point on the right is above the point on the left. So you can see here, XR is greater than XL, and f of XR is greater than f of XL. But it basically means that the point on the right is above the point on the left. And this will apply for any 2 points we pick in this interval from A to B here that you see. So all the way from A to B, any 2 points that we pick, the point on the right will be above the point on the left. And that is what it means for a function to be increasing. Now, decreasing, the definition looks very similar. It says for any two x values, XL and XR, with XR greater than XL, it is the case that f of XR is now less than f of XL. So the only difference with decreasing is that it is f of XR is less than f of XL and not greater than. But still, XR is greater than XL. That means XR is the point on the right and XL is the point on the left. But now the y value of the point on the right is less than the y value of the point on the left. Now, if we look at the sketch here, as we can see, the function is going down as we go from left to right. That's what it means for a function to be decreasing. And now the point on the right gives us a y value that is below the point on the left. Okay? So the y value is going down as x moves from left to right. And again, this applies for any 2 points in the entire interval from A to B. So we can say that this function here is decreasing from A to B. So that's the formal definitions. What you'll notice about these formal definitions is firstly that it's about an interval. It's not just at a single point, but over an entire interval, because we have to look at 2 points in an interval. That's the first thing. The second thing is that we see nowhere in this definition any reference to derivatives or gradients. It's simply about y values being one y value being less than another y value or greater than another y value if the x value is greater than the other x value. So nothing about derivative, nothing about calculus, purely defined in terms of inequalities. Now let us see how this applies to a cubic function like the ones we see in the matric curriculum. So I've got a standard cubic function here with its 2 stationary points. And the question now is, for which interval is this function increasing? Now, when I ask that, we are going to try to find the greatest possible interval for which the function is increasing. And according to the definition I just showed you, that has to be from 2 to 7, including 2 and including 7. So if I can just highlight that on the graph here, it's going to be all the way from 2 up to 7, including 2 and including 7. Why am I including the 2 and the 7? Because obviously, if I do that, the definition will still hold. From 2 to 7, even if I take 2 as my x value on the left, any x value I take to the right of 2, let's say for example I take 3. Now you'll see that the y value for 3 is greater than the y value for 2. Let me draw that in. The y value that we get for 3 is greater than the y value that we get for 2. 3 is to the right of 2. F of 3 is above f of 2. So the point on the right is above the point on the left, even if I start at the turning point. Similarly, let's say I take point 7, the x value 7, the point there, I take that as my point on the right. Anything I take to the left of that, let's say I take 6, you'll notice that the y value for the point on the right is greater than the y value for the point on the left. So I can include 2 and 7 and the definition will still work. That means that we can say that this function is increasing all the way from 2 to 7, including 2 and including 7. Now, if I ask you where the function is decreasing, according to the definition, that would be the part to the left of 2, including the 2, and the part to the right of 7, including the 7. Let's highlight that. So it's this part here, up to and including the 2, and this part here, starting at the 7. Let's test the definition. If we take any point to the left of 2, let's say 1, and then we take the point at 2 as the point on the right, you will see that the point on the right is below the point on the left. So that fits the definition of decreasing, even if we include the 2 there at the stationary point. And if we test here to the right of 7, let's say we take 8 as the point on the right and 7 itself as the point on the left, again you'll see the point on the right is below the point on the left. So the definition for decreasing works all the way up to 2, including 2, and then from 7 again, including 7. So if we summarize our results, the function is increasing when x is between 2 and 7, but we have to include the 2 and include the 7. Or in interval notation, x is an element of the interval 2 to 7, including the 2 and the 7. And the function is decreasing when x is less than or equal to 2, or when x is greater or equal to 7. In interval notation, x is an element of negative infinity to 2, including the 2, or x is an element of 7 to infinity, including the 7. Now, before we get to the section of how all this ties in with calculus, I would just like to discuss with you the formal definition of increasing and decreasing functions at a point, as opposed to over an interval. Now, as you've noticed, the definitions that I gave you initially, the formal definitions, are about increasing and decreasing on an interval. What we would like to do now is look at what increasing and decreasing looks like at a point. Because in calculus, when we use the derivative, we calculate the derivative at a point. And we want to link that with increasing and decreasing. So formally, at a point, it works like this. The function f is increasing at x equal to a. You notice that's a single value. If it is increasing on an interval containing a. So that means if we can find any interval containing the x value a at which the function is increasing, then the function will be increasing at x equal to a. And the same for decreasing. A function f is decreasing at x equal to a if it is decreasing on an interval containing a. Now, if we go back to the example that we've looked at earlier, we will say that the function is actually increasing at 2 because it is increasing on an interval containing 2. You'll remember the function is increasing from 2 to 7, including 2 and including 7. That means 2 is included in this interval on which the function is increasing, and therefore we say that the function is increasing at x equal to 2. And the same for 7. Now, if we look at decreasing, the function is also decreasing at 2 because 2 is contained in the interval from negative infinity to 2. It includes the 2. So that means the function is decreasing at x equal to 2 because 2 is part of the interval on which the function is decreasing. And similarly, the function is decreasing at 7 because 7 is part of the interval on which the function is decreasing. Now what we see may seem very strange to you is that the function is both increasing and decreasing at 2 because 2 belongs to the interval on which it's increasing and to the interval on which it's decreasing. And also, the function is both increasing and decreasing at 7 because 7 belongs to the interval on which it's increasing and to the interval on which it's decreasing. We are now ready to go to the relationship between increasing and decreasing and the derivative. First, I would like to mention that derivative is a point concept. We find the derivative of a function at a point and not over an interval. And that is why it was important that I showed you the definition of increasing and decreasing at a point. If the derivative of a function at point A is greater than 0, in other words, positive, then the function is increasing at x equal to a. Now that's obvious because a positive derivative means a positive gradient. That means the graph is going up as we move from left to right. If the derivative is negative, then the function is decreasing because that means it's got a negative gradient. And so the graph is going down as we move from left to right. Now notice that in these two statements, it doesn't say what happens when the derivative is equal to 0. It says if the derivative is greater than 0, then it's increasing. If the derivative is less than 0, then it's decreasing. But it doesn't tell us what happens if the derivative is actually equal to 0. For that, we have to go further. If the derivative is equal to 0, then we know the function has a stationary point. But then we have to look at what happens before and after the stationary point. If the function is increasing before the stationary point and decreasing after the stationary point, then f is said to be both increasing and decreasing at the stationary point. So increasing before, decreasing after, that means at the point, at the stationary point, it's both increasing and decreasing. And the same goes for the case where we go from decreasing to increasing. Then at the stationary point, it's both decreasing and increasing. Now we say this to make the concept of the derivative tie in with increasing and decreasing in a way that is in agreement with the definitions that we gave. Right? Because remember, based on the formal definitions, we said that the turning points or the stationary points is included in the interval for increasing and for decreasing. So in other words, if the graph goes from increasing to decreasing, at the stationary point, it's included in the increasing part and also included in the decreasing part. So then at the stationary point, we'll say that the function is both increasing and decreasing. But now we have to be careful. There are stationary points where this does not apply. Remember, we get a certain type of cubic graph where the stationary point is also a point of inflection. And in that case, the graph goes from increasing before the stationary point back to increasing after the stationary point, or decreasing before the stationary point to decreasing after the stationary point. And that means that in this case, like this sketch here, where it goes from increasing to increasing, the function is only increasing at the stationary point. And in the case where it goes from decreasing to decreasing, the function is only decreasing at the stationary point. So basically, we have to look at what happens before and after the stationary point, and then come to the conclusion of whether the function is increasing or decreasing or both at the stationary point itself. So this is how we use the derivative to decide whether a function is increasing or decreasing at a specific point. And then in the school curriculum, we extend this from points to intervals. In the formal definition, we first define what happens on intervals, and then from there, we take it to points. But here, we first define what happens at points and then extend it to intervals. So I hope this convinces you that we have to include the stationary points in the increasing and decreasing intervals in the standard cubics, except for these special cubics where the stationary point is also the point of inflection. Now, I said I would explain to you an easy way that we could explain this to the learners, because obviously we can't go back to the formal definitions for most of our learners. It's a bit abstract for the average learner to comprehend. What I found works very well, let us go back to this example that I showed you earlier, is if we say that increasing is like climbing a mountain and decreasing is like climbing down from a mountain. Now, if I ask you, when we climb up a mountain, when do we stop climbing? We obviously stop climbing when we reach the top. So we'll be climbing the mountain from 2 all the way up to 7, and we only stop when we reach 7. We start climbing right down here at 2. We have to start climbing at 2, not after 2. And we stop climbing when we reach 7. So the upward journey is from 2 to 7, including 2 because that's where you start, and including 7 because that's where you stop. Now, if we reach the top, when we climb down the mountain, we start climbing down again at the top. So the top is included on the upward journey as well as on the downward journey. So in that way, it makes sense that we can say that the function is both increasing and decreasing there at 7, because you will climb till you reach 7. So the 7 is part of the upward journey or the increasing part of the function. But you'll also then start climbing down the mountain at 7 again. That means that the 7 is also part of the downward journey or of the decreasing part of the function. I found that this simple explanation works really well for learners. One last thing I want to discuss with you is an issue that's been coming up lately in exam papers, and that's the issue of strictly increasing and strictly decreasing. So sometimes in the exam papers, they ask, where is the function strictly increasing or strictly decreasing? Now, I suppose this was done as a way to try to exclude the stationary points, but actually this is not accurate. The definition for strictly increasing and for strictly decreasing is in fact exactly the same definition that you see here. Some mathematicians distinguish between increasing and strictly increasing, but those mathematicians say fxr is greater or equal to fxl for just increasing. And then when they want to say strictly increasing, they drop the or equal to there. And then we are just left with the definition as I've showed it to you. And even according to this definition, for strictly increasing, the stationary points will still be included. The only thing that happens when we distinguish between increasing and strictly increasing is that strictly increasing rules out cases of constant functions. So in some functions, we have sections where the function is constant for an interval. Now, that would still be classified as increasing, believe it or not, if you use the definition that some mathematicians use where they put the or equal to here. And now, because for many mathematicians that doesn't sound right to say that the function is increasing when it's actually a constant function, they then add the word strictly increasing to rule out that case. But that is not something that we deal with in our school curriculum at all. So basically, adding the word strictly here makes absolutely no difference to whether we include or exclude the stationary points. Even if it says strictly increasing or strictly decreasing, we should in fact still include the stationary points. Thank you for watching our video. Goodbye.